tell you. But this is a completely change of pace. I'll start with a disclaimer and apology. I will not say the word qubit or algorithm except in this statement. And the other thing I have to say is that I know some of you have heard this talk in various versions. I apologize. I hope you'll understand it better. Although it's very simple, it should be transparent both to mathematicians and physicists. I hope there will not be much of an argument after this. So, of course, this is experimental, so I have to thank my collaborators, a great bunch of students. I'll show you their faces instead of the names. So Yoav Lechini and Yaron Silberberg started this job. Yoav actually is now in, both Yoav and Yaron are in better places now. Yoav is at MIT, a Papalardo fellow. Yaron is at Yale. We had to change the group. You know, in 4 years you have to swap. You know, you send all your graduate students away and start with completely fresh batch. So here's the fresh batch. So the people who continue this work is Mor Verbin, Eilon Poem, and Yoni Gilad. So we'll talk about quantum walks. I'll tell you how a physicist look at quantum walk. I really look at quantum walk from a physicist's point of view. There'll be very little computing here. But as you'll see, even physicists had to adjust to a new language and to find some very simple problems nobody has thought about it before in this context. So I'll tell you about quantum walks, not in quantum computing circuits, but really in lattices, in periodic lattices, in disordered lattices. And I'll say a little bit about the effect of interaction in these problems. But before we start, I always feel we have to pay tribute to this person that is much less known than he should be. I guess his face is not very familiar, except to those who heard my talk before. You know his cousin. This is the cousin of Charles Darwin. And he should be not much less known than Charles Darwin, because this gentleman is Francis Galton, and he more or less invented statistics in the way we know it today. He termed some of the basic concepts of statistics. You know, you all use the term standard deviation. That's his invention. You all use we all use correlations as a basic tool to understand statistics and physics. He taught us that correlations are important, and this talk is really, all this talk is about correlations. So we should remember his name. Maybe I should spend a minute tell you why he has been erased from the books of history. He had many hobbies and interests, like this English gentleman of the 19th century. He did everything. He did things from climate to, he's the person who showed the world that fingerprints are individual to every person. He did it by using statistics. He proved, he was really interested to know whether prayers had an effect on the longevity of the people who pray. He proved that there is no correlation. I didn't say anything about the quality of life.
Or afterlife.
Or afterlife. He knows now better. The one thing he did, his real passion, the reason why he's erased from memory, the one thing he invented is the science of eugenics. He was really interested to find whether there is correlation, what is the heredity of intelligence. This is the science of eugenics. It's banned from the books of science, not because it's not a viable question, it's because the Nazis really loved this science and used it in the wrong way. So it's not his fault, but somehow his name is erased. Anyway, the only context in which we know the name Galton today is because of this little contraption that he made to prove, to demonstrate the basic principle of statistics, the law of the center limit theorem. You all know this, or heard about it, I'm sure. It's a board with pegs. You drop a ball, and you look how it trickles down. The ball, as it falls down, performs a random walk. It's like throwing a coin many times and checking what it sums to. And you all know what happens as this thing trickles down, and you do it many times. Eventually, you get a normal distribution centered around the initial point. And you all know that the width of this distribution grows as the square root of the number of steps. This is something he built, and I think in the Science Museum in Boston there's a beautiful machine like this that is hard to take your eyes from, although you know exactly what it will do. So this discussion should start with the question, what would happen if this particle was not a classical ball, but a quantum particle? And you all, I'm sure even the mathematicians here know that the basic rules of quantum mechanics tells you that you should not add probabilities as we added before. For the classical particle, we should add amplitudes. And since there are many ways by which this particle can get to a particular spot, and these ways, since you are not going to look, you don't know which way it will take, therefore you have to add the amplitudes of all these trajectories, assuming no decoherence, nothing bad happens. So you have to add the amplitudes and only then find the probability. And if you do that, the result is amazingly surprising, and it's surprising to many physicists to hear this talk for the first time. It's amazing how this simple thing is not in the mind of most physicists. The distribution completely changes. It's no longer true that the particle will end where it started. It actually ends in a distribution that peaks at two lobes that are the edges of the distribution. And this distribution broadens not as a square root of n, but as n. So it broadens linearly with time, or with the number of steps. And this, of course, has been called quantum random walks by some good people. Some of them will be here. Some of them we saw last week. And it's amazing. It took the principles, of course, are 100 years old, but the idea of a quantum random walk is only 20 years old. We should have some sort of a birthday, I guess, at least for the term, if not for the understanding.
Quantum run celebration.
Second?
The quantum run on Wednesday morning celebration.
Oh, it does? Okay. Yeah, well.
Benny will end up back at their original.
Okay, we'll have to do that. Okay, so my point now is that this is really, although it's amazingly being a new concept, it should have been familiar to physicists, or it has been familiar to physicists for really 80 years or 90 years. Because this random quantum walk is not only performed on pegs of Galton board, but even you put a particle in a lattice. This is a lattice, the periodic array of quantum wells, the simplest model of solid-state physics. You put an electron, say, on that lattice, and you ask how this electron evolves in time, and you can write an equation, and this equation is the tight binding approximation written by Felix Bloch, 1928. And if you solve the equation, assuming that initial condition as you start at site number 0, and you ask how this electron evolves, and lo and behold, you can solve it analytically, and you get a very similar, actually identical distribution to the discrete version we have seen before. Broadening, which is just linear in time, these two lobes that are really dominating the distribution, and these lobes are actually keeping very narrow, they broaden very slowly in time. And this has been called, I think by you, continuous time random walk. It's really even formally equivalent at certain positions. You can prove they're really identical as the discrete version that we have seen before. So again, most physicists are really surprised by this because they've learned this equation, I think, in the first course of condensed matter physics, and they've never seen this. And the reason is that in the physics course, the first thing after you write the equation, the professor says, let's diagonalize the system. And when you diagonalize the system, oops, sorry, I'm in the wrong order, but maybe I erased that slide. Okay, so when you diagonalize the system, what you find is the eigenstates of the entire equation. The eigenstates are spread over the entire lattice, and each eigenstate has its own eigenenergy, and together the eigenvalue, they make a band, this famous sinusoidal band. And that's how you analyze. You say, okay, great, these electrons are free particles, they're sitting on the entire lattice. And somehow this simple exercise of putting an electron on a single site is never solved. Although, because not formally, this solution is saying I'm exciting now a delta function. I'm exciting all the eigenstates at once, and this is what you'll find. So people who study condensed matter physics never think about the electron moving and performs this quantum walk. That's why these terms are surprising, and most condensed matter physicists are not familiar with this ballistic evolution of a single site electron. So it's not easy to put an electron on a site and see how it evolved. That's why, surely, that's why these questions were never phrased this way. We are not going to study this problem not with electrons on crystals, but with light in photonic lattices. Photonic lattices are waveguides made in some substrate. In the simplest realization, they are just parallel waveguides, but each of them contain a single optical mode, but they are close enough together that light can tunnel from one side to the next, and the equation describing this system is just the same tight binding equation that describes electron on a periodic lattice. And we can make these systems precisely. We can fabricate these lattices with exact parameters. We can change both the eigenvalue at each lattice, that's the index of a fraction on each lattice. We can control the coupling coefficient to the neighboring lattice points by controlling the distance. So we have a great control on how to make such systems experimentally. And perhaps the greatest advantage of studying the system is that instead of putting an electron on a lattice in time 0 and seeing how it evolved, now because the system now moves in space, you are now dealing with, instead of initial conditions, with boundary conditions. All I need to do is to shine light on one side and just check how the distribution evolves after a certain distance. So here it is. Here is actually a photograph of the distribution of photons that have performed random walk in such a lattice. Here are the two lobes, everything that we have predicted, in this simple calculation, we can really realize and see it with our eyes. And this system we have been dealing with not to do necessarily quantum walks. Actually, we have been, in my group and in many other groups, we have been studying photonic lattices as a model for condensed matter physics now for almost 15 years, and dealing with many, many problems in condensed matter physics. And every time we did it with classical light. We never bothered about photons. We checked distributions, whether the propagation was linear or nonlinear. This is a bunch of results. And when we realized that quantum walks is really something important and we need to start to think about it, we ask ourselves, okay, what will happen when we really send single photons in these quantum walk, in these photonic lattices? Now here I always like to show, before I start to talk about photons, I always like to show this paper written by Willis Lamb. Willis Lamb is a Nobel Prize winner in physics. I'm not sure which year, but he's responsible for the Lamb shift and Lamb dip, if you know the terms. And he writes this paper called Anti-Photon, and it's not that he predicts a particle called anti-photon, because he claims, let me read to you the first couple of lines. It should be apparent from the title of this article that the author does not like the use of the word photon, which dates from 1926. In his view, there is no such thing as a photon. Only a comedy of errors and historical accidents led to its popularity among physicists and optical scientists. So there is a serious guy telling you, guys, you speak about photons and you think about little balls running around. This is wrong. And I'm telling you this because we are going to say photons now, and I want you to remember that there are certain caveats to the use of the term photon. Particles of light are not the same as electrons, mainly because they always move at the speed of light, and there are several reasons. But for those of you, if you have some extra time, read this paper. It's interesting. It's also an interesting piece of history. You know that photons Well, let me not waste my time on this. We can do that at lunch. So, but you know, we are physicists. We have a formalism how to quantize everything and to quantize the electromagnetic field and to write the equation of light propagating in these waveguides in terms of quantized fields. And this is the Heisenberg equation describing the propagation of the creation operators in such a system. And you do it correctly, and what you discover is, of course, photon. The fact that we send a strong beam of light, still there were many photons there. And when I measure it, it doesn't matter whether I send them the photon by one or a billion together. The distribution will be just the same. The results, whether you send a single photon or many photons, will not be different. So there is no sense in reducing the light intensity in these experiments to very low levels. The results will be just the same. And indeed, every quantum scientist will tell you, or quantum opticians at least, that these systems will, the quantum nature will only be visible when you send not single photons, when you start to talk about correlation. So don't send single photons, send that photons at least in pairs, and start to ask questions about correlations. So this is what we are going to do. Sorry, wrong direction. Yes. What's going on? How does it go? Okay, so we are going. Somebody told me not to use this computer. He knew what he was doing. So we are going to put photons at least in pairs and ask how the pair of photons propagates. And now you'll see that something quantum weirdness start to pop in. So we are going to start with two indistinguishable photons, just the same in every property, but we are going to put them, now depend on how we choose the initial condition. We can put them side by side. We could put them in principle on top of each other or in two separated lattice points. And we ask how these two photons propagate. Now, these photons do not interact. They don't feel each other. The light is so weak, one photon propagates, the other one doesn't know about it. Each of them do their own thing. But still, as you see, the correlation between them matters a lot. So let's start first assuming two photons, just as we discussed, propagating in a perfectly periodic lattice, the ideal case. Now, the reason we'll get strange results is this. Is the fact that these two photons are the same indistinguishable particle. We have no, so if we send one photon here and another there, and receive them, we find them going out here and there, there is no way for us to tell, even in principle, whether this happened or that happened. These are two indistinguishable events, and therefore they interfere. These events interfere, not the photons. It's these two events that we cannot tell between, and we should add their amplitudes. And now photons being bosons, we have to symmetrize them against exchange. If they were fermions, we have to anti-symmetrize, and the whole physics that you'll see now comes from this symmetrization or anti-symmetrization. Some people call this boson sampling. Maybe some people in the audience here, I don't know. So for warm-up, I want to show you how we define these parameters. So let's assume that we put two photons in the same site. So let's call this site number 0. We put two photons, two indistinguishable photons together, and we ask, okay, if we detect one at site number R, what is the probability to detect another one at site number Q? Now, in this case, these two events are the same. Since you started in the same place, there is no difference between this and this. So nothing will interfere in an interesting way. And indeed, if you do this calculation, you find that you get what we call a product state. Really, if you look at the table this way or that way, you see the same thing. It's just each photon does its own thing, and you get sort of symmetric distribution. Here are the lobes. These are the edges that the photons like to travel to. And you see here one went to the left, the other went to the left, one went to the right, the other went to the right, and the two other possibilities. Not interesting. product state is the same. But now let's put them not on top of each other, but one next to each other. And already you get a very different result. You see, the photons now, I remind you, they don't interact. They don't feel each other. They don't know about each other. But they do something completely different. Now, if one went to the left, the other went to the left. If one went to the right, the other went to the right. Not necessarily to the same site. They don't necessarily end in the same site, but they don't like to separate into two regions of space. They never end up in these two distant lobes, just because they are bosons. So for quantum optician to looks at this, they say, oh, of course, photon bunch. Photons being bosons, they like to be together, so they move to the same region of space. This is sort of hand waving, and people, when they see it the first time, kind of feel they understand this. This is not very different. If you take these two photons on a simple beam splitter, that's what they'll do. They don't go together. They don't separate. They always go together. But to show you that it's not just a trivial thing, let's put these two photons into sites separated by one site. And again, these are calculations. Voila, they don't, no bunching. They don't bunch anymore. It's not simple boson thing. But they do something completely different than that. You see, they either get to the side lobes, or they like to be in the center. You see, these regions are relatively empty. So they do a very strange correlation. They draw together a very strange correlation map, which is not simple just bunching or anti. You cannot wave your hand to explain this. It's something that they like to do in this simple system with no clear, obvious explanation.
The plots you're showing are numerical simulation?
Everything so far is numerical simulation, and this too. So since it's numerical simulation, for the same amount of money, I can simulate fermions. Here they are. Fermions, anti-bunch. Of course, fermions should anti-bunch. We know that. This stresses the point that the correlation is strange. But when you integrate these correlation matrices one way, so you eliminate one particle, you just get the density. The particles don't know. Each particle by itself doesn't know that it's a boson and a fermion. The distribution of particles is the same for fermions and bosons. So this was for the two next to each other. Let's put them. This is important. If you ask, what is the distance? So I have two particles, right? They are moving independent of each other. You ask, okay, what if I detected one? How far the other one is likely to be? And you find that fermions move away from each other twice as fast as bosons in this simple initial condition. Again, it's not known. It's amazing how this simple thing was not known 8 years ago. Let's put them with one space in between. You saw already before that bosons do this either corner or center. So what do fermions do in this case? I don't know if anybody here is fast enough with his math, but you'll never guess really. It's something completely different. So now one fermion goes to the side, and the other one says, no, I don't want to be in the side. I will be distributed all around except in the side. So instead you get this strange frame matrix. And again, if you take this or that and you integrate this way, you get exactly the same particle distribution. So it's the correlations that are strange. It's not the distribution at all. Each particle on itself does the simple thing we have solved 10 minutes ago.
But the left integrated one and the right integrated one are different.
Yeah, because here I start them. So this is the integrated result for two particles when they start next to each other, and here you moved a little bit more. So this is not a single particle. This is two particles. With this is the sum on two particles that you start. You ask what is the probability to get a click if I started in this initial condition with two particles with one space away from each other. And here you had two particles separated more. Therefore, the distribution is a little more separated. Okay. Now, although this sounds like extremely quantum, oops.
Sorry, I didn't understand.
No. The answer?
I mean, at the
It's
beginning
when I integrate this.
just to emphasize the question.
In the beginning, you said that they don't feel each other. So it was supposed to be as if there's one particle.
No,
and if
because I start with two. I ask the question you answer with this graph is when I started like this, what is the probability to get a click at site number n?
Mhm.
I don't care. I don't care where the other one is.
Mhm.
So you just move a detector.
But I thought that you were saying that it is as if there was only one particle because they don't feel each other.
Know
No.
which one.
Right.
That's why you get this contribution from both.
My initial condition, I have two particles with this starting condition, and I only ask what is the probability to get a click at site number n. This
It's not the same as shining into one,
exactly. It's like summing a single particle twice.
but shifted. Ah, okay. Shifted by one, and that's
Okay.
not small.
So there is a way, again, most quantum opticians will know this, there is a way to see these things not with single photons, but even with classical light. Again, for the expert who know what Hanbury-Brown twist experiment is, you can see quantum correlations or the echo of quantum correlation in classical light measurement. And this is an experiment. I will not go exactly how it has been done to take a bit. I want to cut on my time, but example with classical light. So there is an echo of these things. Even if I talked about photon correlation, you can see this by measuring intensity correlations. But of course, you really want to do that with photons. We have done that too. This is a collaboration with the group of Jeremy O'Brien, for those who know him. It's not a trivial experiment sending single photons in these waveguides, but it can be done, and it has been done. And again, it's such simple physics that I feel strange to explain why it's not perfect. It should be perfect. But there are reasons to do these experiments, and we can argue about it if you want in the question and answer period. There is another thing. There are things that you cannot demonstrate with classical light. And that's when you send non-classical states, like entangled states. And for example, what I'm showing you here is that if you start with entangled two photons, instead of sending a photon here and a photon there, you send two photons together, either here or there. So the initial state is two photons in 0 or two photons in 1. And now you have a phase to control. It can be plus, it can be minus. And you can switch between bunching and anti-bunching. You can switch between behavior of this entangled pair as bosons or as fermions. So you can simulate fermions with light, which is really neat if you have control on your initial input state. How am I doing? How much time I have? Be gentle. 17. Okay, so we'll talk quickly on interactions. Two photons do not interact, even if you try very hard. Unfortunately, there are now some hero experiments in some amazing laboratories where can you really send one photon and the other photon will feel it and will change, say, its phase because there is the other photon there. This is really hard. It's high-end. It will not going to happen soon in systems like this. But the question can be asked, what if I had enough interaction between these particles so that the energy of putting two particles in the same well will make them feel a different state than if they are separated? The Hamiltonian describing this is known as the Bose-Hubbard Hamiltonian, and it's interesting for many, many reasons. Therefore, if you could measure the Bose-Hubbard Hamiltonian with light, we would have been delighted. Unfortunately, we cannot, but let's simulate what happens. So this is the correlation predicted, right? This is the bunching for 2 photons starting at 0 at 1. This is what we have derived without interaction. And let's just now mathematically in our simulator just increase the value of the energy, so this term. And what you find is that this anti-bunching starts to modify itself and change, and when your energy becomes large enough, suddenly you see that from bunching we move to anti-bunching. These bosons, when they were interacting strongly enough, started to behave like fermions. Again, this is not unknown in certain communities. Here is a simple derivation of this. You see, if you started with real fermions, you almost get the same result, except that here fermions really never get to the same site. Here you see it's not precisely 0. Now in optics we cannot, in my lab at least, we cannot do this with 2 photons. But we can do it with many photons. We can go to the limit. If you have many photons, that n is 10 to the 16, you start to see nonlinear interactions. It's really, there is enough light to change the index of refraction of that waveguide, and therefore you change the energy effectively. Of course, when you have such a huge number, this one is not meaningful anymore, and then you are in what's known as the mean field limit, and you can show, then we can do these experiments. Of course, we cannot count photons, then we have so many of them, but we can do these things in fluctuation of intensities, and we can start to see the beginning of this change. So this is with low field, no nonlinear interaction. You start to increase the field, you start to see this changing happening. So you see at 3 watts, we already have a significantly difference. But when we increase the intensity very much, in the classical optics limit, you just, everything can collapses to a single site. Everything just focuses, generate a soliton basically. While if you could do it with 2 particles, you would have this switching behavior from boson to fermion. So we cannot do that with photons yet. Some people do it with atoms. The world champion in this business is the group of Emmanuel Bloch. This is not the best result they showed, but they are showing how atoms on lattices, which really can interact one-on-one, can show this transformation between boson and fermions. And again, I don't need to explain their results. They should explain their results. They are on the web. Let me end with a connection to disorder. Disorder, is a fundamental problem in physics. Few Nobel Prizes on disorder, and the famous one is for Anderson. What happens when the lattice is not perfect anymore? And the lattice can be imperfect in 2 ways that are kind of different models. You can take the lattice as you had before and just make its depth a little different. So each energy level now is fluctuating randomly. Or you can make the lattice, the coupling coefficient, the tunneling coefficient, different by changing the distances between the sides. In both ways, you'll get to the same classical behavior of Anderson localization. So what is Anderson localization? So just graphically, I want to demonstrate it to you. So suppose you have a perfect lattice. You put your electron or your photon, and this is what we have predicted to happen. This is this ballistic expansion. These are the 2 lobes, as we have discussed before. Now let's put random disorder. And it doesn't really matter which model we choose. We can even combine these models. And yeah, we have screwed up with the parameter. We chose some random numbers for these things, and you get some random result. And you look at this, and it's hard to say anything general. And of course, when you have something which is random, you have to do statistics on the randomness. So just looking at one realization tells you very little. So let's average this over many realizations of this order with the same statistics, and voila. What happens is that you get is what's known as the Anderson localized state with very characteristic, if you could see the cut through this, you will see that it's a state that has exponential decay. And this is actually an experiment we did with classical light, showing this exponentially decaying state that you get by averaging over many realizations of this order. So this Anderson localization is a wave phenomena. I shouldn't say there's nothing quantum about it, but there is no particle nature to it. It's really just a wave phenomena. You can demonstrate it with light, with classical waves, and it's been demonstrated with sound waves and with microwaves, any type of wave you want. People have studied Anderson localization and demonstrated some of these concepts. Indeed, it was a very popular subject a few years ago. Several groups were excited, including ours. This is Moti Segev at the Technion that will be here on maybe Thursday. This is Alana Spez group in Paris, and this is in Guscio, Simon Guscio in Firenze. So all of us measure this Anderson localized state using waves, different types of waves. So now we are ready to ask, after all this 40 minutes of speaking, we are ready to ask what happens when we put two particles, two indistinguishable particles in this system. We should get now this quantum weirdness popping up in Anderson localization. Again, very surprisingly, nobody asked these questions before, and I don't know why. Well, I guess why. Because they were not experimentally viable. Nobody could really tell you where the electrons end after it starts at a certain site. And we can measure that in principle. So I want to show you simulations, not here where everything is kind of nice and already reached kind of a steady state. I'm going to show you simulations here because I want to have a little bit left over from this ballistic expansion that we already understood. This is what we have discussed in a perfect lattice. So here is the correlation map you get when you send two photons, in this case side by side, in a disordered lattice. And of course you get a crazy, disordered correlation map. You look at it, you cannot say anything smart. So you start to average over many realizations of this order, and you wait, and after a while you start to see some order popping up in this problem. Let me jump here. Yeah. So this is a simulations for two bosons co-propagating in this disordered lattice after averaging over realizations. So you see we left a little bit of the ballistic component. Here it is. So in spite of the mess that we inserted into the lattice, and these guys have some problem to find where they should go, but nothing popped up here. The bunching is still there. They like to go either to the right together or to the left together. But they know there is disorder. Sometimes they find themselves locked, and they stay more or less where we put them, near the zero site. So this blob is when the two particles that we put in have stayed more or less where we started. And this is sort of a blow-up of this localized thing. You see, sometimes one particle localized and the other went to the side. These are these 4 points. So this is more or less what we expected in this problem. But these were for bosons. And if you take the same problem for fermions, we saw something that at first thought was a mistake in our code. This is again a blow-up of the situation where two fermions localized in the same together in this situation. And clearly you see this is strange. This is this checker-like pattern, the checkerboard pattern that we get here was completely surprising. What it means, to understand what it means, we should ask what is the distance between two particles. When I send two particles and they end somewhere, they don't necessarily end exactly where I send them. They can move a little bit to the left, a little bit to the right. And I'm asking, where is the other one? If I detect one here, where is the other one? What is the distance between them? And so if you are quick with your correlation maps, this is like integrating this thing this way. And if you do that, you see that bosons as expected, if you detect one here, it's likely that the other one is exponentially unlikely to be away from it. So there is just two exponential tails. But the fermions do this funny thing. They are, for example, fermions never end in the same lattice. They are fermions. They are not allowed to be in the same site. They are more likely to be one site away, but they are more likely to be 3 sites away than 2 sites away. So they have an oscillatory distant function, which was very, really surprising. And we didn't expect that, and nobody else expected that to happen. Again, an extremely simple system known very well for 60 years. So we were sure this is one of this weird fermionic thing. But then when we simulated this situation, where we send these 2 particles with one space in between, and we see this checker pattern in the bosons. So the bosons now have this strange oscillatory distance. So the bosons are more likely to be 2 sites away than 1 site away. Again, completely a surprising result on a very simple physics of a very, really fundamental, one-dimensional, easy problems, easy to simulate, at least with 2 particles for sure. So this is not easy to see. This is not an easy experiment to perform because the key here is to average over many realizations. We have done that with the classical light version of this that I mentioned before we can do. And we have seen here is the oscillatory correlation function, but of classical intensities. This we can do. The photon, the working with real photon is still something we wish to do. A few groups are trying to see that now. It really could be a fun thing to see in such a basic phenomenon of condensed matter physics that has not been seen before. This behavior should be sustained in 2 dimensions and in 3 dimensions as well. So is this quantum computing? I don't think so, but definitely the principles that we see here could be interesting for you guys. Let me, since I have 3 minutes and not 1 minute, I'll mention that what Eddie just told us about evolutions of Hamiltonians. It's trivial for us to do. We don't need to make these waveguides, completely constant from beginning to end. We can easily control the Hamiltonian along the evolution. We have works, which I don't have here with me, but on studying all kind of adiabatic principles demonstrated in waveguide systems. It's very easy for us to generate controlled Hamiltonians using this technology. Temperature is 0, no decoherence, but no interactions. Or at least not easily. So what are we doing? We like to believe that we are sort of studying many-body physics bottom up. We are now at 2. But hopefully we'll get to more as time goes on. Thank you very much.
I have actually 2 questions. One is for the Anderson localization. You showed there the pattern averaged over many simulations, many realizations. Do you have a graph? Do you know how this evolves as a function of the disorder, of the size of the disorder? Because this is for some number.
I cannot tell you quantitatively, but sure, the stronger the disorder. So this is, first of all, we should qualify everything. This is 1 dimension. 1 dimension, so when we started this, our friends from condensed matter physics told us 1 dimension, it's not interesting, everything is localized. Anderson proved that even the tiniest disorder already localizes. But of course, when you start to do these things, you understand that what people know in principle on, again, it's like in these problems that theoreticians solve, but then when you start to do that, even though I have maybe 100 waveguides in my sample, it's finite. So to say that even the tiniest disorder will do localization is really should be qualified. Actually, the stronger the disorder, the faster this position will move. This way you can quantify all that. I don't have it here with me. Yeah. There is another interesting point of one dimension, again for the expert. There is a direct transition, if you can see it here, from ballistic to localized. If you do the same thing in higher dimension, you see an intermediate region where things are diffusive, which amazingly you don't see here. But again, these are all kind of details.
The second question was about the simulating the fermions with photons. What you showed us there was only the end result after a certain amount of time, but the question is how similar is the propagation? I mean, you have there already diffractions from the edge and things like this, so how similar is this propagation along the time?
It's similar. You can prove that in the limit of strong interaction, you can show that this problem goes to the fermionic problem. There is no, there is no edge issue at here. Nothing was interacting with the edges in any of these simulations. So everything was assumed to be infinite.
Can you simulate also more complicated structure like anions or non-abelian anions using?
So you might say that so there is a phase there. I showed you results for 2 summed up or 2. So you can argue that if you put a 90 degrees between them, it's some sort of an anion. I would initially I was very excited about this, but then I think my excitement has been subdued when I realized that this ends with 2 particles. You cannot simulate n particles, n fermions, using n bosons. It's a trick that starts and ends with just 2 particles. So somehow I don't think, at least if you think about kind of quantum simulations, I don't think you can take it to a much more complex systems.
In the beginning, you showed how a classical particle has a Gaussian with root m. Is there a way to continuously go from the wave results to this particle results in the data?
So one of the disadvantages of our system that it's very coherent. It's working with light in this system. You don't have to think about decoherence at all, and the only way to induce decoherence or to move into diffusive behavior is to put what's known as dynamic disorder. Dynamic disorder means not only put disorder, but change the disorder along time or along z. And then you can move from ballistic to diffusive. We have not done this, by the way, but you can easily simulate it. Yeah.
Have you considered the analogy of this type of propagation to Landau-Zinner interferometry in qubits? Maybe, do you know about this? Because it gives very similar results.
So people have demonstrated Landau-Zinner behavior using this system just from the quantum mechanical point of view. I hope I don't remember it. Yeah. Is it here? Yep. Zener tunneling and stuff like that. So people, you can almost open any chapter in Mermin or your favorite condensed matter physics book and demonstrate this with these systems. But the connection to quantum information I know little about.
So in the disorder, when you had just one realization, it seemed much broader than when you average over the realization. So how broad is that? Is that like the square root of n width, or?
I don't know.
Okay.
I don't know. I never checked that.
Last
but
question.
maybe.
It's just the overlap with the localized states, which should be small, with a localization length.
Yeah, I don't see why it should change, but no, I never looked at it, so I don't know.
So basically the question is a bit of a comment. Fermionization only works in 1D. Because in 2D you have a sign problem of basically the whole sort of being able to go around and not achieve the -1 you do in fermions and bosons. You can avoid each other in 2D, whereas in 1D they can't, and that's why it fermionizes. Right. So is there some thought about how to fix that? Is there a trick for 2D?
No, don't fix it. Stay in 1D.
Stay in 1D. It's a good place to be. Yeah.
Okay, let's thank Yaron. Okay, the algorithm for going for lunch is inspired by this talk. It was a random choice. So if you flip your batch, there is this thing, these things, and if you're blue, then you go to Weiss, then you're Weiss, and if you're green, then you're Sherman. And well, you should just catch someone who's with your color and follow. And of course, it's allowed to switch colors. So bon appetit, and we'll meet here at 2:20.